Okay, let's unpack this. You take thousands of breaths a day, often without a second thought. But what exactly is in that invisible, life-sustaining substance all around us? Today, we're taking a deep dive into something so fundamental it's practically taken for granted, the very air and atmosphere that surrounds us.
And a truly intriguing aspect here is just how much crucial detail lies, beneath the surface of something we interact with constantly. We received a fascinating stack of sources covering everything from the precise chemical makeup of air to its, surprising historical discovery, its vital uses, and unfortunately the serious challenges it faces in modern times. Our mission today is to extract those essential nuggets of knowledge so you walk away truly well-informed about the air we breathe.
Exactly. From surprising historical experiments that really redefined our understanding to the silent heroes of the atmosphere, we're going to explore how air isn't just nothing, but actually a dynamic, life-giving mixture. Get ready for some aha moments. So we often imagine air as just empty space, right? Or maybe a simple element, much like people believed for centuries. But our sources make it abundantly clear. Air is far from simple. It's an incredibly complex mixture of gases, invisible and transparent to us, of course, because all those gases are colorless, and it literally blankets our entire Earth, stretching hundreds of kilometers above us.
And what's truly fascinating is how we figured that out, how that understanding came about. It wasn't until 1774 that Antoine Lavoisier, with a stroke of genius, really proved air was a mixture. He did this through a very ingenious experiment. He essentially trapped air over heated mercury.
Right, and here's where it gets really interesting. His observations were just groundbreaking. He noticed a red layer forming on the hot mercury. And crucially, the mercury level inside the bell jar rose by exactly 1/5 of the total volume. It was such a clear sign that a portion of the air had been, used up, consumed.
Precisely. And his conclusions from that simple observation were profound. That 1/5 portion of air that was used up by the mercury, he called it active air, later naming it oxygen. That was the part that supported burning and, vitally, life itself.
Okay.
The remaining 4/5 he initially called azote, which means unsuitable for life, and that became nitrogen. It didn't support burning. This simple setup fundamentally changed how we understood our world, didn't it?
It really did. And you can actually see this mixture concept in surprisingly simple everyday activities, even at home. Can you maybe walk us through one of those everyday proofs, one that really drives home this idea that air is a mixture?
Absolutely.
Yeah.
Think about a burning candle. It's a classic demonstration. If you light a candle, place it in a shallow dish of water, and then cover it with an inverted glass jar. The candle burns for a bit, then it flickers out. It extinguishes.
Yay!
And here's the kicker. The water level inside the jar will rise. It rises by about 1/5 the jar's height. That 1/5 represents the oxygen that was used up by the flame, proving it's a distinct component.
Oh, I see.
The remaining 4/5, of course, that's the inactive nitrogen. So this visually confirms air is a mixture, not just a single element.
That's so clear. It really makes it tangible. And you also mentioned earlier that the components of air can be separated without changing their chemical makeup. How does that work?
Well, if we connect this to the bigger picture, it means that air isn't a compound, where elements are chemically bonded together. It's a mixture. So its composition isn't fixed. It can vary slightly. And its components keep their individual properties. They don't change chemically just by being mixed. So we can separate them physically, for instance, through a process called fractional distillation. This is where air is cooled way down until its different gases liquefy at distinct, very low temperatures. That allows us to separate them without any chemical reaction or energy exchange.
Got it. So what exactly is in this invisible dynamic mixture then? By volume, our sources break it down pretty clearly. Nitrogen makes up the vast majority, about 78%. Oxygen is next, about 21%. And then argon, that's a significant chunk too, almost 1%, 0.9% to be precise. It's the most abundant inert gas.
Right. And then you have carbon dioxide, a tiny but really crucial fraction, around 0.03% to 0.04%, plus variable amounts of water vapor depending on humidity, and then even smaller amounts of other inert gases like helium, neon, krypton, and finally impurities, things like dust particles, smoke, even germs, all mixed in. What's truly remarkable about air's composition isn't just the numbers, though. It's how this precise recipe, mostly invisible nitrogen, and that life-giving oxygen creates the perfect conditions for life as we know it. Each component, even the tiny ones, plays a highly specialized and essential role.
Okay, so with that understanding of air's basic makeup, what makes each of these invisible ingredients so incredibly vital? Let's maybe start with nitrogen, since, as we just heard, it makes up the bulk of our air.
Nitrogen, yeah, it's colorless, odorless, tasteless, and slightly lighter than air. Crucially, it's neither combustible nor does it support combustion, which, raises an important question. Why is azote, meaning unsuitable for life, so vital?
Right. Seems like a contradiction.
Well, we can't breathe it in and use it directly from the air like oxygen. Its role in the nitrogen cycle getting into plants and then into us is fundamental for building proteins, and its role in just diluting the oxygen is absolutely critical.
Absolutely.
Think about it. Without all that nitrogen damping things down, oxygen would be far too reactive. Even small sparks could quickly become raging, uncontrollable fires. Essentially, nitrogen is the unsung hero that prevents our entire world from becoming a spontaneous bonfire every time someone strikes a match.
That's a powerful way to think about it, a global fire blanket almost. So nitrogen isn't just a diluter, it's also a fundamental building block. Tell us more about its critical roles in, say, life and industry.
Well, as I mentioned, it's vital as a nutrient. Plants need it for protein synthesis. They fix it from the air or soil. Then animals and humans get it by consuming those plants. It's essential for life. Industrially, it's used in manufacturing essential fertilizers, things like urea, ammonium sulfate, helping grow our food. It's even used in making explosives like TNT. And in the food industry, nitrogen is often used to flush food packages. Think about those bags of potato chips. Flushing with nitrogen removes oxygen, which prevents bacterial growth and keeps the food fresh for longer. And liquid nitrogen. It has incredible cryogenic uses. Preserving blood, tissues, biological samples in hospitals and labs.
Fascinating. Okay, let's move on to oxygen, the active life giver. About 21% of the air. Beyond the obvious breathing, what are some of the most surprising or foundational ways oxygen truly powers our world, from the smallest cell to the biggest industries?
Right, oxygen. Like nitrogen, it's colorless, odorless, tasteless, but it's slightly heavier than air. And it's slightly soluble in water, which is absolutely critical because that's how fish and other aquatic life breathe. Interestingly, when you cool it down enough to liquefy it, it actually becomes a distinct pale blue color.
Oh, cool.
But its primary significance, chemically speaking, is its role in oxidation. That's the process where it combines with other substances. And this happens in two main ways. Quickly, like in combustion burning, where fuels combine rapidly with oxygen to release energy. Heat and light. That powers so much. And it also happens slowly, like in our own bodies during respiration. Living organisms oxidize food molecules, slowly releasing energy to live.
So what does this all mean then? Oxygen isn't just about taking a breath. It's like this invisible engine powering nearly every facet of our modern world, from saving lives in hospitals to blasting rockets into space.
Exactly. In medicine, you have oxygen cylinders for patients with breathing difficulties. There's also something called carbogen that's mostly oxygen, about 95%, with about 5% carbon dioxide. It's specifically used to strongly stimulate breathing in certain situations, and it's used with nitrous oxide for anesthesia. Industrially, huge applications. Oxyhydrogen and oxyacetylene flames produce incredibly high temperatures, like 2,800 to 3,300 degrees Celsius, perfect for cutting and welding metals. It's used to remove impurities like carbon when making steel. It acts as an oxidizing agent in manufacturing chemicals like nitric acid and sulfuric acid. And yes, liquid oxygen, LOX, serves as a powerful propellant fuel in rockets. It's the ultimate multitasker.
Incredible. Okay, then there's carbon dioxide, CO2, present in a very small quantity, but seems mighty in its uses.
Very much so. It's colorless, odorless, non-combustible, and it doesn't support combustion. Its most critical natural role, without a doubt, is in photosynthesis. Green plants absolutely need it to make their own food. They pull it from the air.
Right, the basis of the food chain, really.
Absolutely. But it also plays a vital role in minimizing heat loss from Earth's surface.
This is where we get the greenhouse effect, right? Where certain gases, CO2 included, act like a natural blanket.
Exactly. They trap some of the sun's heat that radiates back from Earth's surface. They reflect it back down. This keeps our planet warm enough to sustain life. Without this natural greenhouse effect, Earth would be a frozen wasteland.
Makes sense. So it's essential, but too much is a problem we'll get to. What else is CO2 used for?
Well, because it's heavier than air and doesn't support burning, it's used in fire extinguishers. It sinks down onto the fire, forms a blanket, and cuts off the oxygen supply, smothering the flames.
Clever.
In the food industry, it's used in baking soda, or sodium bicarbonate, which releases CO2 to make bread and cakes rise. And as dry ice, which is simply solid carbon dioxide, it's fantastic for preserving perishable foods like fruits, vegetables, and meats during transport. Keeps things very cold without getting them wet. It also puts the fizz in carbonated drinks, obviously. And it's a raw material for manufacturing chemicals like washing soda and fertilizers like urea.
Okay. And water vapor. Moisture in the air. Seems simple, but crucial.
Absolutely crucial. Its presence, which varies a lot depending on location and weather, fundamentally determines climatic conditions. Things like rain, snow, mist, dew, fog. They all depend on the amount of water vapor in the air. It plays a huge role in the continuous water cycle, evaporating from oceans and lakes, forming clouds, and returning as precipitation.
Right. And what about those inert or noble gases? Argon, helium, neon. They make up almost 1%.
Yeah, argon's the main one, about 0.9%. These gases are called noble or inert because they are chemically unreactive. They generally don't combine with other elements. This lack of reactivity makes them perfect for specialized uses where you don't want chemical reactions happening. For instance, helium is used in weather observation balloons because it's so light and won't react or burn. Neon gives those bright advertising signboards their distinctive reddish-orange glow when electricity passes through it. Argon creates an inert atmosphere inside electric light bulbs, preventing the hot filament from burning out quickly by reacting with oxygen. Some rarer ones like radon are radioactive and used in certain cancer treatments. Xenon and krypton find uses in specialized photography lighting.
Wow, specific jobs for specific gases. And even dust particles have a role.
They do, though they seem like just dirt. These tiny particles suspended in the air are actually vital. Water vapor needs something to condense onto to form clouds and eventually rain or snow. Dust particles provide those surfaces called condensation nuclei. So no dust, potentially no clouds, no rain.
Huh, never thought of it that way.
But of course, an excess of dust particles is a pollutant. It can cause respiratory problems. And like greenhouse gases, dense layers of dust can also trap heat near the surface. So it's a balance.
Okay, this paints a picture of a finely tuned system. But you mentioned pollutants. While air is essential for life, human activities are increasingly attacking its quality. This shifts us to the very real problems of air pollution and its consequences. This is something that impacts us all directly. Expert, what are the primary sources of this threat?
Well, air pollution does arise from some natural sources like volcanic eruptions releasing ash and gases, or forest fires, or even pollen grains causing allergies. But overwhelmingly, the major sources today are human activities. We're talking about the massive burning of fossil fuels, coal, oil, natural gas for energy in power plants, homes, and industries. Vehicle emissions are a huge contributor, especially in cities. Industrial outputs from factories releasing various chemical fumes and particles. Deforestation is a big one too, because trees are natural air purifiers, absorbing CO2. Fewer trees means less purification. Even agricultural chemicals like fertilizers and pesticides can become airborne pollutants. And simply burning waste releases harmful smoke and gases.
It's a long list, and the effects are serious. Let's maybe look at some of the major pollutants and their impact. What about suspended particulate matter, SPM? What does that include?
SPM includes a whole range of tiny, solid, or liquid particles suspended in the air. Things like smoke, dust, soot from burning. It can also include things like lead oxide particles, especially from older fuels or industrial processes, asbestos fibers, and natural things like pollen grains. The big problem is these particles are small enough to be inhaled deep into the lungs.
And that causes what?
That leads to a range of respiratory problems: asthma, bronchitis, silicosis from silica dust, other lung diseases. It reduces visibility, creating haze or smog. More alarmingly, some particulates are specifically toxic. Lead oxide from automobile exhaust, for example, has been linked to brain damage, particularly in children. And pollen grains, as many allergy sufferers know, can trigger uncomfortable, sometimes severe allergic reactions.
That's quite concerning. Then there are the oxides of carbon. You mentioned CO2 earlier, but what about carbon monoxide, CO?
Carbon monoxide, CO, is a different beast altogether. It's produced by the incomplete combustion of fuels. When there isn't enough oxygen for fuel to burn completely to CO2, think car engines running inefficiently, or burning coal or wood in a poorly ventilated stove or fireplace. And CO is highly poisonous.
Why is it so dangerous?
It's deadly because it binds very strongly and essentially irreversibly to the hemoglobin in our red blood cells. Hemoglobin's job is to carry oxygen from our lungs to the rest of our body. If CO binds to it, hemoglobin can't pick up oxygen anymore. The blood's oxygen-carrying capacity plummets. This quickly leads to oxygen starvation of tissues, causing headache, dizziness, confusion, and eventually unconsciousness and death. It's a silent killer because it's odorless and colorless.
Chilling. And carbon dioxide, CO2. You said it's not poisonous itself.
Right, CO2 isn't acutely poisonous like CO. We exhale it all the time. But the issue with CO2 is the sheer quantity we're adding to the atmosphere, primarily from burning fossil fuels. This excess CO2 is the main driver of global warming, enhancing that natural greenhouse effect we talked about. So understanding these pollutants isn't just academic, is it? It connects directly to public health and the global environment.
Absolutely. It's frightening to think that the air itself can carry such threats. What about the oxides of sulfur and nitrogen? SO2, NO2, where do they come from?
These mainly come from burning fossil fuels, especially coal and oil, that naturally contain sulfur and nitrogen impurities. When these fuels burn, the sulfur reacts with oxygen to form sulfur dioxide, SO2, and sulfur trioxide, SO3. Nitrogen in the fuel, or even nitrogen from the air itself at high combustion temperatures, forms various nitrogen oxides like NO and NO2. Industrial processes like smelting metal ores can also release significant amounts of SO2.
And their effects.
These gases are also highly problematic. They are poisonous and act as respiratory irritants, aggravating conditions like asthma and bronchitis. Hydrogen sulfide, H2S, another sulfur compound sometimes released, has that characteristic rotten egg smell and is also toxic. Nitrogen oxides contribute to the formation of ground-level ozone or smog, which harms lung function and vegetation. And critically, both sulfur dioxide and nitrogen oxides are the primary culprits behind acid rain.
Okay, let's deep dive into acid rain for a moment. How exactly does it form from these pollutants, and what are its most devastating effects?
Acid rain forms when SO2 and NO2 released into the atmosphere react with water, oxygen, and other chemicals suspended in the air. They get converted into sulfuric acid, H2SO4, sulfurous acid, H2SO3, nitric acid, HNO3, and nitrous acid, HNO2. These acids then dissolve in water droplets in clouds, making the rain, snow, fog, or even dry particles that fall significantly more acidic than normal.
And the damage.
The damage is widespread. It damages wildlife, particularly in aquatic ecosystems. Acidic water kills fish, insects, and other life in lakes and rivers, making them barren. It harms plant nutrition by damaging leaves and altering soil chemistry, leaching essential nutrients like calcium and magnesium, and releasing toxic metals like aluminum. This makes the soil acidic and less fertile, stunting crop growth and damaging forests. It also corrodes metals, think railway tracks, bridges, exposed pipes, accelerates their decay, and it severely damages buildings and historical monuments, especially those made of marble or limestone, which are calcium carbonate based. The acid literally dissolves the stone over time. The Taj Mahal in India, for example, is famously suffering from this effect, sometimes called marble cancer, due to air pollution from nearby industries turning its white marble yellowish and causing pitting.
That's terrible. A direct assault on our natural and cultural heritage. And then there's global warming, a term we hear constantly. Can you quickly clarify what it is and how it ties into these air pollutants?
Sure. Global warming refers to the long-term heating of Earth's climate system observed since the pre-industrial period due to human activities, primarily fossil fuel burning, which increases heat-trapping greenhouse gas levels in Earth's atmosphere. The main greenhouse gases responsible are carbon dioxide, CO2, methane, CH4, nitrous oxide, N2O, and certain synthetic chemicals like chlorofluorocarbons, CFCs. These gases act like the glass in a greenhouse, or maybe a more relatable analogy is the inside of a car parked in the sun.
Right, it gets much hotter inside than outside.
Exactly. The sun's energy comes in as visible light, warms the Earth's surface. The Earth then radiates some of this energy back out as infrared heat. Greenhouse gases in the atmosphere absorb some of this outgoing infrared radiation and re-radiate it, some back down towards the surface. This trapping of heat warms the planet. While some greenhouse effect is natural and necessary for life, adding extra greenhouse gases enhances the effect, causing the Earth's average temperature to rise. This isn't just about slightly warmer weather. It leads to significant changes in climate patterns, sea levels, and extreme weather events.
Okay, so CFCs were mentioned there too. They also deplete the ozone layer, right? What's the impact of that?
Yes, chlorofluorocarbons, CFCs, which were widely used in refrigerants, aerosols, and solvents, have another damaging effect. They rise into the stratosphere and react with ozone molecules, O3, breaking them down. The ozone layer high in the atmosphere acts as a natural sunscreen, absorbing most of the harmful ultraviolet, or UV, radiation from the sun. When the ozone layer is depleted, more UV radiation reaches the Earth's surface. The impact of this increased UV exposure includes increased rates of skin tanning and, more seriously, skin cancer in humans. It can also cause cataracts in the eyes and potentially suppress the immune system. It can even cause snow blindness, a painful temporary loss of vision due to UV reflection off snow or ice. It also harms plant life and marine ecosystems.
Wow. Multiple serious threats from these pollutants. With such serious threats to our air quality, let's shift our focus to solutions. How can we all contribute to preventing air pollution? It can feel like such a huge global problem, but what can we actually do?
It's true, it's a massive challenge, but there are actions at both collective and individual levels. Collectively, some key measures include growing more trees and protecting existing forests. Plants are amazing. They absorb CO2 and release the oxygen we need. Reforestation and afforestation are vital. Industries need to install tall chimneys to disperse pollutants higher up. But more importantly, they need effective filters and scrubbers to trap solid particles and harmful gases before they're released. For vehicles, developing and using more efficient internal combustion engines is important. Catalytic converters are crucial as they help convert harmful pollutants like carbon monoxide and nitrogen oxides into less harmful substances before they leave the exhaust pipe. And of course, shifting towards cleaner energy sources away from fossil fuels is the big long-term solution.
Right, the big picture stuff. But connecting this to you, the listener, there's actually so much you can do individually every single day, isn't there?
Absolutely. Individual actions really add up. For starters, try not to burn waste materials, things like paper, garbage, dry leaves, plastics. Burning releases smoke and poisonous gases. Instead, composting organic waste is a much better option. Reduces waste and creates useful fertilizer.
Good point. What else?
Be mindful of electricity use. Don't misuse it. A lot of electricity is still generated by burning fossil fuels, so saving energy reduces emissions at the power plant. Simple things like turning off lights, using energy-efficient appliances. Try to avoid using plastic bags. Their production often involves fossil fuels, and their disposal, whether by burning or landfill, contributes to pollution. Reusable bags are the way to go. Plant more trees whenever possible. Even a single sapling in your yard or community makes a small difference. If you own a vehicle, get it checked regularly for pollution levels. Ensure it's well maintained to run efficiently and cleanly.
Keep surroundings clean. That seems basic, but important too.
Yes. Proper waste management prevents litter from being burned or ending up polluting waterways. And try to motivate others. Encourage friends and neighbors to adopt these habits. Maybe advocate for using cleaner cooking fuels like LPG or biogas instead of firewood or coal, especially in areas where that's common, as indoor air pollution is a major health hazard.
That really makes you think about daily choices. Maybe consider transportation options too, like walking, cycling, or public transport instead of driving alone.
Definitely. Choosing cleaner transport options whenever feasible makes a direct impact on local air quality and greenhouse gas emissions. Carpooling is another good strategy. The broader implication here, connecting back, is that preventing air pollution isn't just some abstract global issue handled by governments and industries. It really starts with the choices each of us makes every day.
Every small action truly adds up. That's a hopeful note. Okay, we've explored air's composition, its vital roles, and the critical challenges it faces from pollution. But to truly appreciate its delicate balance, maybe we need to take a quick look at the chemistry of its most active player, oxygen. We know it supports life and burning, but how does nature manage to keep its levels so constant, around 21%, despite all this consumption?
That brings us beautifully to the oxygen cycle. And it really is, as you implied, a remarkable balancing act. It's nature's way of recycling this essential gas. Think about it. Living organisms, us included, constantly use atmospheric oxygen for respiration. Every breath we take uses oxygen. And oxygen is also consumed whenever fuels burn campfires, car engines, power plants. Plus, some oxygen gets locked up in the formation of nitrogen oxides during lightning or combustion. Yet, despite all this continuous consumption, the amount of atmospheric oxygen remains remarkably stable over time.
So how? How does this incredible balancing act happen? What replenishes it?
The answer, in a word, is photosynthesis. It's all thanks to green plants, algae, and some bacteria. They continuously return oxygen to the atmosphere during this amazing process. Essentially, they take in carbon dioxide from the air and water from the soil or surroundings, and using energy from sunlight, captured by the green pigment chlorophyll, they convert these simple ingredients into glucose, their food, their energy source, and crucially, they release oxygen as a byproduct. The equation is basically carbon dioxide plus water plus sunlight yields glucose plus oxygen.
So plants are essentially breathing out the oxygen that we breathe in.
In a manner of speaking, yes. It's truly a gift from the plant kingdom to virtually all other living beings on Earth. And the astonishing thing is the scale. The rate of oxygen production through photosynthesis globally is so much faster, so much greater than the rate of oxygen consumption from respiration and burning combined. This huge output from plants ensures that natural balance, keeping the oxygen levels stable and replenishing what's used. It's nature's perfect, large-scale recycling system for the air we breathe.
Wow. You can even demonstrate this quite visually, can't you? With an aquatic plant.
Yes, there's a classic experiment, often done in biology classes, that shows this beautifully. You take an aquatic plant, like hydrilla or elodea, place it in a beaker filled with pond water, and cover the plant with a glass funnel, inverted. Then you fill a test tube completely with water and carefully invert it over the narrow stem of the funnel, ensuring no air gets in. You place the whole setup in bright sunlight for a few hours.
And what happens?
You'll start to see tiny bubbles rising from the plant leaves and collecting at the top of the inverted test tube. This gas pushes the water level down inside the test tube. Once you've collected a decent amount of gas, you can carefully remove the test tube, keeping it inverted so the gas doesn't escape. Then you take a glowing splint, a piece of wood that's been lit and then blown out so it's just glowing red at the tip, and you insert that glowing splint into the mouth of the test tube.
And it relights.
Exactly. It bursts back into flame. That's the definitive test for oxygen. It's a clear, powerful demonstration that the plant, through photosynthesis powered by sunlight, was producing oxygen gas right before your eyes. Seeing that really brings the oxygen cycle to life.
What an absolutely incredible deep dive that was into the very air that sustains us. We've journeyed from, the historical discovery of its actual composition, figuring out it wasn't just one thing, to the intricate dance of all its components, the vital roles they play, then the critical threats it faces from pollution, and finally these amazing natural cycles, like the oxygen cycle, that work constantly to keep it balanced.
Indeed. It's quite something when you stop to think about it. From understanding why that huge amount of nitrogen is actually essential, preventing our world from just spontaneously combusting, to recognizing the crucial role of that tiny, tiny percentage of carbon dioxide in maintaining Earth's temperature just right for life. The air is far more dynamic, far more complex, and far more intelligently balanced than it appears at first glance. The insights from these sources truly highlight the interconnectedness of our planet's systems and just how dependent we are on this invisible ocean of gas above us.
So here's something to think about next time you take a deep breath. Really feel it filling your lungs. Consider this. How might this newfound understanding of air's intricate composition, its delicate balance, the threats it faces, and the cycles that sustain it, how might that change the way you interact with your environment and perhaps even inspire a greater appreciation, maybe even a sense of awe for every single molecule you inhale?
That's a powerful thought to leave you with. Thanks for joining us for this deep dive. We really hope you feel more informed, maybe more curious, and definitely more connected to the world around you, right down to the air itself.